can be depending how you. If I was to review,
You get
how
chances.
for 342.
You can take a class 3 times before you kick out of the major, right?
Did he?
I think so. That's what it says in like the student handbook.
The major focus classes or just math, physics that apply to me?
See, I think for C-STEM, you can fail a class 2 times. You have to pass it a third and then they reevaluate what the value is.
To be honest, if you fail a class once, you're like 1 year behind.
Yeah.
Like Cal 2, if you had failed Cal 2, you're gonna be 2 semesters behind. That's rough.
I got
I feel like if you do all your homework and stuff, it's hard to get it tomorrow.
That doesn't apply to every class.
No, you're right. Yeah.
She really just called me.
Like you said, if you do all your, not if online doesn't.
Right, yeah.
Yeah.
This because it's a good job, it doesn't mean you know how to do it.
Unless you had those contacts, like Google Contacts, and like you're looking around.
So it is 9:30. We can start. And today we're going to cover some more finite state machine examples as practice. The finite state machines will not be on your quiz on Wednesday. It will be covering sequential logic and sequential logic timing. So your homework plus what is a D-latch? How do you make a D-latch? How do you make a flip-flop? Things like that. But your next quiz will be on finite state machines. So we're doing some practice now. All right, so just as a reminder, if we have this finite state machine diagram, we just want to cover how do we go to the excitation table. So we're just going to fill this out. So the first thing, is this a Mealy or a Moore? Moore, why is it Moore?
Because what's inside the circle, right? The input and output states, or the output stays inside the circle. I don't know what I'm saying.
The output state is always inside the circle. What is the key difference?
I think it really has it on the lines.
Oh, you don't mean the output state, you mean the output.
The output, right?
Yeah, the output, yes. The output is only defined by the state, not the state and the input. So we can see that if we're in state 0, output is 0. If we're in state 1, output is 1. State 2, output is 1. State 3, output is 0. So we can immediately fill in the output part of this, right? State 0, output is 0. State 1, output is 1. State 2, output is 1. State 3, output is 0. Right? And then now we need to figure out the transitions. So if I'm in state 0 and my input A is 0, where do I go? If my input A was 1, where do I go? And now if I'm in state 1, input is 0, where do I go? No, I'm in this state, this one, right?
Sure.
And my input is 0. So A is 0. Where does the arrow that tells me A is 0 point to? Yeah. Right, it's right here. And the direction of the arrow is important. So this one is going from state 0. All right, and then if A is 1, and now if I'm in state 2, A is 0.
There is no A, no A going zero.
So what does this arrow with no condition mean? Yeah, just always go to 1, 1. Right? It doesn't matter what A is. And then if I'm in state 3, now where am I going? Yeah, 0, 0. So I just wanted to review this diagram, make sure we all were able to look at it and understand it. All right, so here is a little bit different of analysis. Rather than the diagram, now we're given this circuit diagram, right? So this one they're saying is Q0, this one is Q1, and then output Y is Q0 or Q1. So what type of machine is this? Mealy or Moore? What does output Y depend on? Not quite. What are the inputs to the OR gate? Not D latches, but flip-flops? And the flip-flop store, which are? Yeah, the state bits, right? And then our input into the machine is A, right? So my output Y depends only on the state. So that means it's a Moore machine, right? So it's a Moore machine. So then one of the easiest things to do is just calculate the outputs. So Q0, so for if I'm in state 0, my output is 0, right? State 1, output is state 2, state 3. 1, 1. Right? 1 or 1 is 1 still, right? All right, so now let's look at our next states. So if Q0, Q1 are both 0, then that means I'm taking A naught. And then A is also 0, so I'm going to take Q0 naught. So this is a 1, and then this is a 1. And Q0 is a 0, so no carry in. And then A is 0, so we're taking the 0 here. So Q1 becomes yes, right? 0 into Q1. And then Q0, 1 plus 1 plus 0 gives me what? Yep, so 0, and then the carry is 1. So Q0 is just 0. And now all the same thing, except now A is 1. So if A is 1, Q1 becomes Q1, and Q1 was 0, right? So Q1 is still 0. And then over here, if A is 1, we're selecting Q0. So this is 0. This is 0. I'm selecting A naught. A is 1, so this is 0. So this would be 0, right? Okay, so then what else is here? So Q1 is 0, Q0 is 1. So 1, 1. Q1 is 0. A is 0. So this is 0. And then A is 0. So Q0 naught. And Q0 is 1. So this is 0. So Q0 becomes 1. 0 plus 0 plus 1 is 1 with carry of 0. Q1 is 0. A is 0. So this is 0. Now if A is 1, Q1 is still 0. So Q1 still is 0. Well, what changes up here? So if A is 1, Q0 is 1, this becomes 1. A is 1, this becomes just Q0, which is 1. 1 plus 1 plus 1 is 1. Carry 1. Right? And then we can keep going. So if we have 1, 0, that means Q0 is 0, Q1 is 1, and A is 0. So if A is 0, we know that Q1 is going to be 0. So let's just fill that out. So Q1, if A is 0, it becomes that. And then if A is 1, Q1 becomes Q1. So that solves that part. Now we can just look at the top part. So A was 0 first, Q0 naught. This is 1, Q0, 0. A naught, A was 0. So this is 1. 1 plus 1 is 0, carry the 1. Right? Now let's change it to A is 1 now. So Q0 is still 0. Still 0. A is 1. This is 0. A is 1. Q0. This is 0. So we get 0. Now Q0 is 1. A is 0. This is 0. A is 0. So Q0 is 1. So we have a carry of 1. I mean, yeah, carry in is 1. So 1 plus 0 plus 0. 1, carry the 0. And now if A is 1, we get Q0, so this is 1. And then this is A is 1. So this is 1. So again, 1 plus 1 plus 1. 1 carry the 1. So we can fill out this table from the circuit diagram as well. Right? All right. So this one is where you're going to start doing your practice on your own. So we want to design a sequence detector that detects 2 different sequences. So we're going to use 2 separate FSMs that both have the same input A to keep the design simpler. So FSM1 has an output X and FSM2 has output Y. X should be 1 if A has been 1 for at least 3 clock cycles altogether, not necessarily consecutively. Y should be 1 if A has been 1 for at least 2 consecutive clock cycles. And this one is 2 consecutive clock cycles. So first, just do FSM1 with output X. That's it. Don't do FSM2. And you're going to first make your diagram. Then you're going to make your state table. Then with your state table, you can make your excitation table. And then with your excitation table, you can make your K-maps and make your next states and output equations. And with your next states and output equations, you can draw the schematic. Don't do E. Yeah, well, let's say don't draw the waveforms. You can still do E. You can just say for each input, what is the output? Is all. Okay. So this one should take a little bit of time. Do the first one as pairs. So don't start on your own for this. Do this one, work together. Make the finite state machine 1, the output X.
Maybe we should do this. At the sentence. I think that last should be. Different. At the sentence. Yeah, but the output. Output wise. I don't know what it is. Just. Goes back. Sorry. Almost.
So it's usually 0.9101. Yeah, almost 10 says it doesn't have to be. So what if you have also one that's. Yeah, about so let's say for example, the 0, because that's the 0. So it doesn't have to be consecutive. So there's not a lot of controls. Like, I mean, for at least 3 contexts. Like, I know, like, if this is 0, 3, if this is 1, it doesn't matter if it's 0 or 1, you're still in the. No, it doesn't leave back here. Because it's not. Once it reaches 3 complex, you have to. When you say themselves, you can say themselves. We can just let us know. So what do you do? So you have 1, 1, 1. Then what do you do for the state? It's not, but it says. It goes back to the destroy. You can have 0, 1. So if you have 1, so this goes to. You want just again, these all. And then go wide. It's just. So is not as it reaches. That's what you're talking about. It's why. So maybe more. That's what I know. Didn't have the right. I know. Well, you're saying that's already great. Oh, I guess like. Yeah. That's what you're saying. That's correct. Yeah. One woman. And then this is the IQ market. Where's your A9? A9. Okay, yeah, A9. Yeah, that was the thing. That would be computed. Sure. What if you guys go back there and spell it? Oh, you you get 1 year, 1 year and it's just we do 2 different 2 separate. So you're trying to do all that. It's dependent on WS. Actually, you've never so X you never go back. X you never go back. Yeah, you just go back. X you just go forward and you're there. You just move to the same state. It keeps funding experiments. I'll say so if it's 0, go back to the same state. Yeah, if it's 1, it's a loophole. Yes. And that's until it reaches the very one, then it is. Yes.
So inside the Moore diagram, what do you put inside here?
You drain your.
Yeah, when these.
Thank you. You don't have.
Yeah.
Almost even.
So this is the your output.
Whatever is inside that.
So this would be zero, or would it be, or, well, I mean, yeah, something is zero.
Yes.
So zero, zero. Okay, yeah. Okay, that makes sense, yeah.
Then you have to rate.
Okay. Yeah.
Stop it.
That's not so bad. Okay.
Go back to it. When I say it, state, I mean, anything.
Coded state
If
transition.
you talk about one, two, three,
I need to put-
anything other than.
That's what we just did. Yeah, okay, okay.
You don't have any.
So, yeah, let's stay back. Session. So, ID.
Make the very last one. Part of that.
I wish that I had two monitors.
All together, not necessarily, all together. So, as long as it works, as long as that 3 days, they work, and then correct. Instead of infinitely looping.
Yeah, that makes sense.
But this, what you're having to do is you're setting. You don't want to have that. Because I'm thinking, it's. To me, it's. Don't wait once forever.
So, yeah, because A's are should be one. If they have been one.
Yeah.
So it's basically looping around each process until it gets to eight. I guess zero is like it's pretty big.
That's a great thing.
Yeah. So they 100 drops.
And they could not. Yeah.
And Biden has a nice recording of the line.
It looks just like that, yeah. So, yeah, STX. This is gonna learn. Well, actually, this is one for you. That's weird. Yeah, it should be like. So state now.
Let's have it affected visually. I don't know. The shop.
Well, how is it? Which is a phone.
It's a group.
Is it through the phone?
Either funded by.
Okay.
Yes.
Now it's Russians, and that's why it was the example.
Well, those are. Yeah. I'm looking for the word that shows.
Yeah.
Okay.
In terms of state transition.
So here's just current state, so state table, current state, next state. And so D and A, then you just.
No, it's three, two, one, two, zero, A is there. No, happening first.
The current state. That's zero.
Is the state transition?
That's the state transition.
Oh, this one, I don't
Yeah.
Happens for
Okay.
And then we're doing the full board.
It's not in the state machines. Function fast.
And it looked like this, right?
Yes, we understand that. Just think our state.
Well, you're gonna-
It's we don't know. Say it.
First one is gonna be.
Okay, so you list out all, so it would be zero, zero, zero.
Zero, one,
I'm all zero.
zero.
I think there's one side, one column.
Well, what do you think?
That means it's zero, it's time, that's a place long, it's zero.
See how they have, so you have all. Sides, so, I don't, okay, so you have,
Like this, you know.
that's zero, zero, and then this is the next thing.
That's what our table looks like.
A, Q1.
And then this is
Does it matter when you
the
do
next.
it?
Would you not have a
Okay, so I see what it's doing. It's like going,
error?
is that what we're supposed to do?
No, it's not. Yeah, just.
Yeah, I was just trying to figure out what the annotation is.
If you put Q1 to 0, A,
What?
Q1 to 0, A, or A to Q1 to 0.
So this statement is zero.
Yeah. Is Q the? Q?
If you are circles inside.
Yeah.
Right.
And then A is
So we put, so what do we put in this? Is what I'm trying to figure out. So this is your in.
I think it's. Yeah, we don't fight those.
So this one's different. This thing that it has these different annotations. Annotation divisions. Or is it, oh, this is for the.
But then, so you can select
shoulders.
I love.
What's the, so this is the state table and this is the annotation table. And we'll put a state transition table. Just this one.
I think even this. And out.
K.
Oh, okay. Do we have to do one for, Q?
I think it's.
Just, yeah.
these are things we don't have to worry about. So you don't have to see it.
You only have a simple.
For this case.
So,
For the Q's.
Right. So you can just use you can apply that or something. So that could just be base.
This is just A, right?
it'd be,
That's right. That makes sense. And then this is,
it'd be, you know.
this is Y.
A.
So when Q is zero,
So. we don't have a system, like,
Yeah, I think you guys are still mostly working on this, but we do need to go over it just so that we can finish in time. Just for your, make sure that you get it. If you haven't already, the code for today is 077. So do answer just anything to that. And let's work on this problem now. So first thing is deciding on what kind of machine to make. I am going to make a Moore machine. So let's call this S0. This is our initial state. Let's also consider this as the state where we have seen 0 ones, right? So that means if I see input is 0, I stay here, right? S1. A little bit. So S0, I should output
0.
Yeah. And if I see 1, 1,
That's state.
go to the next state, right? If I see as S1, I should output. My output if I'm in S1, 0, right? If I see a 0, where do I go? S2, output is
0.
Zero.
if I see a 1 in S1, where do I go? So S2 means I've seen 2 1s, right? And then S3, what do I output? Right? So if I see a 1 from S2, where do I go? And there's my 3 1s. Not necessarily consecutive, but I've seen 3 1s, right? And then if I'm in S3, I just stay in S3. no matter what, right? Okay. So then let's make this table. And let's use the standard convention. S0 is 0, S1 is 1, S2 is 2, S3 is 3. So I need 2 bits for my state, right? So if I have, why am I drawing it as this? So D1, D0, and then inputs. What did they say input was called? A. So 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. And then I need to handle Q1, Q0, and output X, right? So output X, let's just do that one first. I'm always 0 except in state 3, right? If I'm in state 0 and I get a 0, I stay in state 0. If I get a 1, I go to state 1. If I'm in state 1 and I get a 0, I stay state 1. Otherwise, I go to state 2. If I'm in state 2, I get a 0. I stay state 2. Otherwise, I go state 3. Yes. We're a Moore machine. So we only depend on the current state.
Gotcha.
Okay, and then if I'm in 1, 1, I just stay in 1, 1, right? So now that I have this table, I can create my K-maps, right? So my K-map for X is fairly simple. I don't even think I need to draw the K-map. What is my equation for X? Yep. D1 and D0. That's it. All right, so now the other ones are a little bit more complicated. Let's actually draw these K-maps. So 0 through 2. Okay. So let's draw them this way. So D1, D0, A. This is 0, 0, 0, 1, 1, 0, 1, 1, 0, 1. So 0, 1, and 2. So 0, 1, and 2, right? Yes. And then we have 1, 1, 1, 1, 1, right? So this is for Q1. I'm circling this, and I'm circling this. So what is staying the same across my big circle? Yes, D1. And what else? So what are my 2 things that are changing? So what is my equation? Right? And then what is changing across my other circle? Yep. And well, no. Oh wait, yeah. So what is my equation here? No.
Just D1 and D0 are changing.
Oh wait, I'm sorry. I wrote this wrong. What is changing? And
Big circle or small
the
circle?
little circle.
D0 stays the same and A stays the same.
Yeah, so it's D0. A, what do I need here? Do I need to invert any of this? Or is this right?
No, they're both.
Yeah, so it's right. So D0 and A. So this is my equation for Q1, right? My minimum 2-level logic. Q0. And then again, D1, D0, A, 0, 1. I have 0 is a 0. And then 1 and 2. So 1, 2. And then 3, 4. So this is 3, this is 4, and the rest are 1. Right? Is this what you guys have? I'm just double checking because I'm doing this as we go. All right. So I'm circling this, I'm circling this, I'm circling this, right? Q0. Let's do the one that's across first. What's staying the same? What's staying the same? Yes, D0. A, what does D0 need to be? Right? Because it's staying as 0. All right, my vertical circle, what's staying the same? And do I need to add any inverts? And then my last circle, what stays the same? So now I have all of my equations. I can draw the circuits, right? First things first, I have 1, 2 bits. These are flip-flops. This one is, let's call it Q1. This one is Q0. And then my output X is just the and between them, right? We found that out over here. Yes. Uh-huh. Over here. Because this one is corresponding to this circle. A is staying the same, and A is 1, and then D naught is also staying the same, right? Here and here, but it's 0. So it needs to be D naught and A. Okay. So then let's do Q1 first. So it's D1 or D0 and A. I mean, yeah, D0 and A. And then we need to have this OR gate. So D0 comes from over here. And I don't need to invert it. A comes from inputs. And then we OR with D1. And this is into Q1. Right? My other equation, I have 3 AND gates. So here is 1, here is 2, here is 3. All of these go into this OR gate. This goes into Q0. So I need D1, D0. So D0 is right here. I need D1. That is right here. And then I need D0 not. So I need to invert. And then D0 is, again, right here. And I need A. A is just input. And then I need D0, A not. So this is D0. Here is A not. This is my circuit. Right? So we just follow all of these steps. We get the digital logic circuits that implements the finite state machine. AND gates, AND gates, AND gates, AND gates, OR gate, OR gate. D1, D0. Q1, Q0.
The AND gate at them?
Hmm?
That's an AND gate at them?
Yes. So what you guys can do now is finite state machine 2, right? Same process. You can do it as practice. We don't have time to work on it today in class, but there's also this example that you can work on as well with a larger K. So on Wednesday, we'll cover your next lab. Next lab should be finite state machines, right? And you also have your quiz. And again, quiz is going to be on sequential logic and sequential logic timing. And your homework is due before next meeting as well.